I'm very happy to introduce John Greenlees from Warwick University, and he is going to talk about the singularity category of CBG for a finite group G.
Hi, good evening. I'm very happy to be with you in Sydney. I've been wandering around your campus as much as you can at the moment, so I got something of a feel for it. But I wish I was there in person, but one day. Okay, so I wanted to talk about the singularity category for the cochains on BG, well, so I'm going to tell the story as if it's about a finite group, but actually, I mean, you could tell the story about being about a certain class of algebras that you can approach, a bigger class of algebras that you can approach, of which this is one example. I think it's easier to motivate if we do it this way. So this is going to include joint work with Greg Stevenson and Dave Benson, and I've written up the 3 archive papers there if you want to get more details. Okay, so we're going to start with G, which is well, you should think of it as a finite group, but sometimes I'm going to let it be a compact Lie group, but I'll tell you when. And we're going to have a field K. You might make it the field with P elements, perhaps, field of characteristic P. And we're going to look at, well, the representation theory over K. So, one thing we could do to understand that is look at the cohomology of the group. So I suppose starting in algebra, I'd just be looking at the X algebra. So this is telling you about resolutions of K. And so if you understand this as a ring, you understand some things about representation theory of G. For example, most crudely, how quickly a resolution begins is reflected in the dimensions of these things. But I'm going to really take a topological point of view. So I'm going to think of this as the cohomology of a space, the so-called classifying space of G. And if you want, you can take the bar resolution of K and realize that, and that gives you BG, and then you can take the cohomology. But anyway, this is really going to be a given ring. It's going to be a ring that we think about, and well, it's a graded commutative ring, well, it's a very special ring. So that's the main message here, special ring. And probably the first thing, it's a special ring whose structure reflects the structure of the group, but not going all the way back. It's a special ring, and for example, if it's Cohen-Macaulay, it's automatically Gorenstein. This is a result of Benson and Carlson. If cohomology of BG is Cohen-Macaulay, it implies it's automatically Gorenstein. So that's special. But if you didn't want to assume it was Cohen-Macaulay, if you localized at a minimal prime, it would be Gorenstein there as well. But still, there are these unpleasant conditions, and the first message is that we shouldn't be thinking about the cohomology of BG at all. We should be thinking about the cochains, a sort of a refinement. The message is consider instead the cochains on BG. So you can think of this as singular cochains of a space, or actually you could probably think of this as cochains. You could take an algebraic model of the cochains and consider that, as long as you are prepared to import some, well, whichever way you look at it, you've got to import some technology to talk about it. And technology isn't really the subject of the talk, so I'm not going to say a lot about it, but I will think of this as a commutative ring. So this is a commutative ring. so as a commutative ring. So some of you will know that actually you cannot construct this as a commutative DGA if P is not 0. So what I must mean commutative in a homotopical sense. So I really mean that it's an E-infinity ring. And actually, for those of you who like these things, I'm thinking of it as an E-infinity ring spectrum. And really, this means the function spectrum of maps from BG to an Eilenberg-MacLane spectrum. So it's really an E-infinity ring. But the message really is we can work with it as if it's a commutative ring, provided we only do things which are in a homotopy invariant way. Okay, so that's what I want to consider instead. Well, the message here is, in fact, it's always Gorenstein. So cochains on BG, if you look at it this way, is always Gorenstein. No condition about being Cohen-Macaulay first. But of course, you've got to work out what you mean by Gorenstein in that setting. You've got to give a homotopy invariant version of that. And I suppose this is a result of mine with Dwyer and Iyengar. But anyway, the point, which I'm not going to dwell on, the point is that it's better to think about cochains on BG than the cohomology ring. And that's what we're going to do. So hence, study cochains BG as a commutative ring. I mean, when I say commutative ring, I mean a commutative local Noetherian ring. And commutative means graded commutative. Okay, so supposing we are thinking about it as a commutative ring, perhaps the first thing we'd look at is, when is it a regular local ring? So that will feature later on the talk, but I will tell you that cochains BG is regular. So we have to, we'll work through this later. We have to give it an appropriate definition if and only if G is p-nilpotent. So any P group has cochains BG being regular, but p-nilpotent, it means it's there's a normal complement to your Syllov P subgroup. So anyway, think of all P groups, cochains BG is a regular local ring. So here we have, on the one hand, we've got G p-nilpotent, and those are always, so this is the group G, and this is cochains BG, and p-nilpotent, these are the regular ones, and then all finite groups are Gorenstein. So obviously those are a smaller class, and the point of the talk is to look at this gap and try and understand how good cochain BG is for various different groups. Sometimes it'll be better, sometimes it'll be worse. So what do? We take the leaf out of the commutative algebra book and and recall the definition of the singularity category. So if R is a conventional commutative local Noetherian ring, then the idea is we look at the singularity category of R, and that measures how far you are being from regular, because you look at finitely generated modules modulo finitely generated projectives. That is to say, you look at the bounded derived category, homotopy category, or look at chain complexes over R, all of whose terms are finitely generated. So chain complexes of finite complexes of finitely generated modules. So that's the bounded derived category, modulo the homotopy category of finite complexes of finite generated projectives, perfect complexes. So usually you write dB over well, dperf or dc of R. So, and this this does the job because of the theorem of Auslander-Buchsbaum-Serre, which says that you can characterize regular local rings by the fact that any finitely generated module has a finite resolution by finitely generated projectives. And so for a regular local ring, this dB is the same as dc. So this is dc R is trivial if and only if R is regular. So it is, and let's call this Auslander-Buchsbaum-Serre. Okay, so that's the starting point, really. We'll run over some of that later on. I mean, it turns out that the good properties of singularity category, they're better when R is Gorenstein. So we are in the ideal situation to start talking about this. So the point of the talk is do this for cochains BG instead of R. So there's going to be some problems there because we don't know what a finitely generated module is. So we can't even make the definition. So make the definition. So but these are the tasks, if you like. Make the definition, and that'll take us a little while. And then the second step is to actually check that you still characterizes the regular local rings, the vanishing of it. So dsing characterizes regular local rings. So I suppose that's just a check on the definition being a sensible one. And then, well, the main point of the talk, and I hope we're going to get to talk about this, is you can actually calculate the answer in at least one class of cases. So, calculate the answer, calculate dsing cochain VG for, well, at least when G has a cyclic Sylow subgroup. So this is of course, that's only a very special, very special case, but I mean, it's quite a rich answer, and I hope we're going to talk about that a little bit. And roughly speaking, so you can just you'll see, you know, the first 2 points were in my paper with Greg Stevenson, and this bit is with Dave Benson. Okay, so that's really, I've just described what I'm going to do. I'm going to try and do A, B, and C, and perhaps this is the moment to pause because I can't hear whether it's quiet in the audience or you know, is the muttering. Have you questions?
I'll just say if people have questions, but they are shy, they can also send it to me and I'll ask John.
Great. Thank you. And don't be shy to interrupt either. Let me go this way. Okay, so I was going to start the next section, which is to talk about, so what's the strategy for understanding what I'm now trying to do is give a definition. So regular case. So the strategy is that we can understand the regular case first and then use that to tell us what to do in the general case. Okay, so well, we started with cochains on VG, and we're thinking of it as a commutative ring in a suitable context. So that means we can look at modules over it, differential graded modules over it, or I mean module spectra over it, if you're thinking that way. And then we can look at the homotopy category of the module category. This is the homotopy category of modules. So that's going to be our context. And you remember what we were trying to do. We were trying to look at the bounded derived category modulo the perfect complexes. So perfect complexes are characterized by being what I'll call small. Some people call them compact. Well, DC objects are in DC if and only if they're small, by which I mean n is small. This is the definition. M small if m is small if, and when I map it into a sum, well, there's a natural map from the sum of the MNIs, and this is an isomorphism for all test objects. So that's a categorical thing. Oh, I'm writing, I'm using homotopy theorist notation. So I'm going to work in a homotopy category. So I'm using square brackets for morphisms. Okay, so hence we've defined that automatically gives us a definition of the, I should call them, anyway, equals small objects. So we can define the denominator in the definition. So let's see if we can at least understand something. So special case, we can understand what happens if the cohomology ring is polynomial. So if the cohomology ring, which of course is the homology or homotopy of cochains BG, is polynomial, well, or more generally if it's regular, but let's just stick to polynomial. So then I can tell when things are small. Then if pi star m, so m is a modulo of the cochains on BG, is finitely generated, so it's finitely generated modulo of a polynomial ring, then m is small. So, well, the point about this is what one way of obviously getting a small object. Let's just think about the proof. So obviously the ring itself is small because when I map, if I take up here, if I take M to be the ring, then of course I just get the sum. Therefore, anything you can build from, therefore, anything finitely built from cochains BG is small. So all I've got to do is prove that the M I've got is finitely built. And so what do? Well, I use the result in algebra, which says that I can get a I use Ausländer Buchstaben sehr. I use the fact that I can get a finite resolution of finitely generated objectives for pi star m, and we're local, so they might as well be free. So I've got a finite resolution, and then I realize it, and then realize. So what in cochains BG module? So this is a finite resolution in modules over the cohomology of BG. So now I realize it in cochains. So what do? I first of all say each Fi is free. So it's a sum of copies of the cohomology of BG suitably suspended. And so I can realize it by just replacing the cohomology by the cochains. And then, for example, I start building M in the same way that my algebraic resolution was built, and then build. Well, I mean, you probably know how to do this, but let's just look at the first step. The point is, I'm going to have to begin by, I've got my M, and I want to map from F0, and that's going to be the first step of my construction. And so I need to know about maps from a free module, so any free module, into M. And of course, I can just take homotopy, so that gives a map to pi star F, pi star M, which is just taking pi star. And this is mod coms over cohomology of BG. This is an isomorphism because it's obviously an isomorphism when F is a free module on one generator and therefore all. Okay, so continue. So anyway, so we've got a supply of small objects here. Okay, so that's enough for us to say, to give the definition. So I haven't yet defined what it is for cochains BG to be regular. So it is regular if, well, so I've been keeping on quoting Alexander Buchsbaum's there, but in fact, of course, I only need to test on a single module. If K itself, K has if I was in commutative algebra, this was just an R module, R would be regular if and only if the residue field has a finite resolution by finitely generated projectives. So I'm going to take that if K is small. So we already have an example of, so hence, well, example. I've just argued that if the cohomology ring happens to be polynomial, so if this is polynomial, it's polynomial. So for example, G might be, I guess it doesn't happen that much, but if G was an elementary abelian 2 group, product of copies of group with 2 elements, the BG would be a product of copies of RP infinity. This would be a polynomial ring. Then cochains BG is regular. This is because K is obviously finitely generated as a module over a polynomial ring, and so I can use this example up here. So actually, I should have at the beginning of this section said I'm often going to permit G to be a compact Lie group here. So actually, I don't need very many compact Lie groups. So let me say this remark. All so far, all of section 2 works for G a compact Lie. I think, and the compact Lie groups that I might mention, actually, I just probably want to say G is, I mean, it might be a finite group, that's perfectly good compact Lie group, but I want to also include U of N, or you might want to consider products of circles. Products of circles. And that would give us some more examples because, of course, the cohomology of BUN is polynomial on the Chern classes. And if I had a product of circles, the classifying space would be a product of complex projective spaces, which would be a polynomial ring on degree 2 generators. So there are a few examples like that. Okay, so but how do we understand this more generally? If there was no more examples, there wouldn't be any point to this discussion. So the key here is to think now use so now use Morita theory. So in other words, if I was in commutative algebra and I had my ring R, I think the definition of regular now says I should start thinking about, R studied via, resolutions of K. So that's like saying the X algebra of k into k. So as soon as little k has got a finite resolution by finitely generated projectives, then this X algebra is going to be finite dimensional. So that's the remark we're going to use here. So, well, let's call this a fact because it's going to come back a lot. What happens if I do this for the cochains on BG? Actually, let's do cochains of any space X of K, to K. So this is the bit of topology I'm going to quote. So this is the Eilenberg-Moore spectral sequence, says that this calculates the loops, base loops on X, at least as long as it converges. So this is Eilenberg-Moore. Let's not call it a fact, let's call it Eilenberg-Moore. This is true provided it converges if, well, the classical example is if X is simply connected, but that's not going to be enough for us. But I've implicitly been using coefficients in K. That's all the time. So K is a field of characteristic P, or if X is connected and pi1 X is a finite P group. So crucially, that's going to cover some of our cases. So example, what happens if X is BG? Well, so this is still not quite true. If X is connected, pi1 is a finite P group and X is complete. It's P complete. I mean, the point is that it's obvious that the left-hand side is invariant under maps which are mod P homology isomorphisms. Therefore, I might as well replace X by its completion. So, if I take X as BG, this will not usually be P complete. So I have to P complete it. So then we've got Hom cochains BG. I mean, the point I'm making is that the cochains on BG, by definition of completion, is the same as the cochains on the P completion. That's P completion is well, it's not quite a universal example of it isn't quite the universal example of a space with a map from the original space, which is a mod P homology isomorphism. But in particular, it does have that property for nice enough spaces. So Homs of cochains BG of K into K is the chains on the loops. Now, on this side, we will see later, it's very important to complete it. Because if I didn't complete it, we know what the loop are. If I didn't complete it, loops on a classifying space, I mean, the loops reverses taking classifying spaces, so this would just be G back again. And G is mostly a finite group, so this would just be a finite set of points. But we'll see that doesn't happen later. So here we have, so now we've seen, so hence, corollary, if you like, cochains BG is Gorenstein, sorry, is regular, if and only if the homology of the loop space on the P-completed classifying space is finite dimensional. So I'm taking a few steps here because what have we done? We've looked at, we've said the definition of being regular is this K should be small, that is finitely built out of the ring. So therefore, this whole thing will be finitely built. Maybe I should keep a record of this. So this is if the cochains BG finitely builds K, that means that HOMS of the cochains BG K cochains BG finitely builds the thing that we are actually caring about. But this thing is obviously just a copy of K because it's HOMS out of a ring to something. So in other words, if it's regular, then I can finitely build chains on loops from K. So its cohomology or homology is finite dimensional. And well, at this point, I'm going to just quote the result. So hence, cochains BG regular if and only if G is p-nilpotent. So this is, well, at least some of that is obvious. So if G was a P group, then when I take BG and complete at P, the completing at P does nothing. And so when I take loops, I just get back a finite set of points. So obviously a P group has cochains BG being regular, and maybe that's enough to be going on with, but the general full statement is this. Okay, so that's supposed to be the regular case. We've now understood it. Let's see, I've got a little bit time before the break. So what this will let me give a definition for a finitely generated module. So remember what we're trying to do. We're trying to define the singularity category, which is finitely generated modules modulo small modules. We've understood small modules, and we've understood that for regular things. Let me write. This is 3 finitely generated modules. Okay, so the idea is that I know that I want the Auslander-Buchsbaum theorem to be true. So for regular rings, regular local Noetherian rings, regular rings, finitely generated is the same as small. And so that's going to be my starting point. So hence, so we take this as definition for cochains on BG when it's regular. The definition of finitely generated. So what are we going to do in general? We're going to compare it to this. So we have to, for an arbitrary G, a normalization. So what am I doing here? I'm remembering the Noether normalization theorem, which says that under some minimal hypotheses, any commutative Noetherian ring is finitely generated as a module over a polynomial subring. So a normalization of cochains BG is, well, let's a homomorphism of groups from G to U, which is faithful, so a faithful map, so an injective group homomorphism, so that, well, I want 2 things. I want to say that cochains BU is regular, and cochains BG is small as a module. Of course, this induces a map from cochains BU back to cochains BG, and as such, I get cochains BG being a module of cochains BU if this is small. So that's a normalization. And of course, the classical, there are two examples here, which we'll use both. So if G is a P group, then the cochains on BG is already regular. That was the easy case of the red statement in the box. Then the identity will do. I should have called this nu for normalization. Then nu equals the identity from G to G will do. And the second example is, well, I could take a faithful representation in a unitary group. Can take u equals un because I'm n, and u is a faithful representation. So then, of course, I've already told you the cohomology ring of BUN is polynomial. So therefore, it cochains on BUN is regular, and well, we can either, because it's a classical theorem of it's probably classical theorem of Venkov that the cohomology of BG is finitely generated as a module of the cohomology of BUN, and then we can use our example. So and use the classical theorem that cohomology of BG is finitely generated over cohomology of BUN. I mean, actually, what you're really doing is you're using the fact that there's the fiber, the homotopy fiber of a map from BG to BUN is UN mod G, and that's a finite complex. That's the proof of it. Anyway, so we have normalizations in all cases, but of course we've got a massive choice of them. But at least let's make now the definition. We say that a module, I can now define finite generated modules over cochain BG. So if M is finite generated over, if M is a module, is a cochains BG module, I would say M is finitely generated over cochains BG. Of course, this doesn't have a meaning yet. I'm defining it. I can't define it like that. I say relative to nu. So I pick a normalization, and then I can say finitely generated relative to nu if M is small over cochains BU. We've got the map from cochains BU back to cochains BG, and so I can just restrict M to being a module over cochains BU. Okay, so it's a definition, but unfortunately it seems to depend on things, well, you have to work quite hard to say that actually it didn't depend on anything. So let's see. I think I should have an example. In fact, we've got so if the cohomology of BU is polynomial, then we have a criterion for when a module is small. So I want to say then a cochains BG module is finitely generated if its cohomology, if its homotopy is finitely generated over the cohomology of BG. So I should is finite. The cochains BG module is finitely generated relative to the particular nu we just chose, G to U, because well, pi star m finitely generated over the cohomology of Bg means that it's finitely generated over the polynomial ring, the cohomology of Bu, and we knew that we've already checked that that means it's small. So actually, as long as we chose a polynomial normalization, this means something extremely concrete. And it would be possible to have given this talk just starting at this point with that as a definition. But somehow I think that would be unsatisfying.
Is there always a normalization?
Yeah, there's always a normalization. Let's have a look. So if I've got any group, it always has a faithful representation. Any compact Lie group, we definitely are restricting to nice groups that way. Then it does have a faithful representation in some unitary group, and so that'll do.
And what does miracle flatness say in this world?
What is what?
Like miracle flatness?
I have no idea what you're talking about.
You know, like this crazy thing that Cohen-Macaulay rings, if you have if it's finitely generated over some subring, then it's automatically flat over that subring.
I'm sorry, I don't. I mean, that's a good. I mean, that's an interesting question, but I don't know at all. Flatness. What?
Because it looks very close to, like in commutative algebra, if you had this Noetherian normalization, then it'd automatically be flat over that.
Right. I see. So I'm just thinking about flatness. I mean, finite flat dimension I can imagine knowing about, but I'm not sure how I'm going to define flatness in a derived setting. So I'm going to think about that. So miracle flatness, you called it.
Yeah, I think that's what I've heard it called. I'm not sure if people know other terms for it.
Great. Well, I'm going to think about that because that sounds interesting, but I don't have a clue. Okay. However, I observe it's not at all obvious that if I'd taken the first example of normalization, if I'd started with a P group, it's by no means obvious that that if I take an object, a module over it, so if G is a P group, I mean, it's certainly not obvious that if its homotopy is finitely generated over the cohomology of Bg, then actually it's small. It's not at all obvious, but I'm just about to tell you it's true. So the theorem, possibly one of the main theorems of my paper with Greg, is that actually this is what's another thing? This is independent of nu. Finite the definition. So for any G, finite generation is independent of normalization. And therefore, by the example I've just done, and hence M is finite generated over or nu finitely generated, let's say, for any nu is nu. Sorry, that's a nu finitely generated if and only if pi star m finitely generated over cohomology of Bg. So that being finite, having homotopy which is finitely generated over a conventional module is something we can actually check. Okay, so I'm certainly not going to prove this theorem. I mean, it it involves setting up a sort of apparatus of Gorenstein context, because the cochains on BG is Gorenstein for all G, and cochains BU is Gorenstein, and then we can have a map which is relatively Gorenstein. Using all that sort of structure, you can work out how push forwards and pullbacks work, and use a large apparatus to then check this. Okay, so I'm certainly going to use the conclusion, right, so maybe I need to make the definition explicit. So hence we say M is finite generated if it is nu finite generated for some nu. And now we know what that means. Okay, so the corollary is that D6. Oh, now we can define D6. So that's the thing. The other half of that definition that I definitely need to make. D-sing for cochains BG. So we now have a definition of the homotopy category of finitely generated modules. Because we know what they are, and the homotopy category, of course, of small ones. And of course, I'll probably use the notation which says the top thing is DB, cochains BG, but that's the definition. And DC. Okay, so actually, well, let's have the corollary is that D-sing cochains BG is trivial if and only if cochains BG is regular. And well, let's just make this proof explicit. Let's say we've got two normalizations. So, well, one way round is easy. Which way round is that? Oh, this way round is easy, clear, since obviously K obviously lives in the upper thing. It's obviously finitely generated. Therefore, it lives in the bottom thing. Therefore, it's small. Is finitely generated, and hence, by vanishing, it is small. And that was the definition of regular. The other way around, we have to take two normalizations. I'd have to say, so take the identity is one normalization, G to G. Oops, that's an entity. That says as one normalization. And we could take G to U as a polynomial, as polynomial normalization. Okay, so now I want to say, so now I've got to show that any finitely generated module is small. If M is finitely generated, then pi star M is finitely generated over cohomology of BG, and hence using the independence, since G is regular, it's small over cochains BG. Okay, so actually there's one more fact that I'd like to get into the first part, and then it would be a very good thing to break. I just want to make the general observation. This is one more general result before we get into the specific case of G with cyclic Sylow subgroup. So here's the general fact. I guess we're going to call this a theorem. Also, with Greg, and this is the BGG correspondence, which says that d sing cochains BG is the same as the co-singularity category, or I mean, of. So it's relating the singularity category of cochains BG with its causal dual, the chains on loops. Well, I'm going to write it this way and then explain. Cosing of chains on loops on BG completed. So by which this is supposed to mean the bounded derived category, the homotopy category of finitely generated modules over chains on loops BG, which we haven't actually defined, but you define it the same way. I defined it here, modulo the small ones. Sorry, modulo the ones with finite dimensional homology. So maybe I'll do this way. Homotopy category of M with pi star M finite dimensional over K. So this is the thick subcategory generated by K, if you like. There is actually, that's the one we're really going to use, but let's just mention, you can go the other way as well. The cosing of cochains BG is the sing of chains on loops on BG completed in P. And the reason for mentioning that is I'm saying this is like the BGG correspondence. You're supposed to think of, in the BGG correspondence, I might be thinking about this second one, and I might take G to be, I might take G to have polynomial cohomology. So then the chains on loops on it would be an exterior algebra. So I'd have the singularity category of an exterior algebra being a co-singularity category of a polynomial algebra, but then by the famous theorem of Serre, if I take quasi-coherent modules over projective space, that is the same as taking the bounded derived category of modules of that polynomial ring modulo finite dimensional ones. So that's so this is the point is it's the BGG correspondence in this homotopy theoretic context. And I am definitely going to use this first statement when we get to this the special case.
John, do you know if there's so there's this beautiful theorem of Quillen that tells you what the cohomology ring looks like up to homeomorphism?
Absolutely, yeah. Yeah.
And is there some kind of, you know, is there some hope of doing such a thing for cochains on BG? I'm not even sure.
Well, I mean, this is what I mean. People spend their time trying to understand the Balmer spectrum of various types of ring, and so you can recover the spectrum of the cohomology of BG by doing things at a homotopy level, if you like.
Mm-hmm.
So I mean, Quillen's theorem, I was telling you actually that you just need to know the set of elementary abelian subgroups of G, and then you can identify the spectrum of cohomology of BG up to homeomorphism, and people try to do that. So you have to work out what you mean by elementary abelian, and so for various classes of generalized groups, I mean, so you can try and look at groups in a homotopy theoretic sense. So p-compact groups are the analogues of connected compact Lie groups, but then there's p-local finite groups which come down to doing doing representation theory like Pooch did, and so that's already quite well developed. And then there's p-local compact groups, which are supposed to be the both of those. So p-compact groups are completely classified like connected compact Lie groups. It's a little more complicated, but they're classified. But in these other classes, they're very big class, bigger than the actually algebraic ones, and people try to prove things in those contexts which are analogous to the ones that were proved by Quillen and others for the groups themselves, and with some success. But it's hard work. But for cochains on BG itself, that's we're actually pretty close to algebra. You can still go back to that. I'm not sure if that answers the question. I'm just going to summarize what you need to know from the first half, which is almost nothing. So that's good. So you could forget most of that. So we're talking about the cochains on BG for G a finite group. It'll be finite almost all the time. And then this has Kossel dual, which is the chains on the loops on the p-completed classifying space. I think that's the first thing we need to know. And then we need to know the definition of the singularity category, which is supposed to be the homotopy category of finitely generated modules over the cochains on BG. And so most of the first half was about what that should be, but it's the thing you first thought of anyway, which is that the homotopy should be finitely generated over the homotopy category of small modules. And then there's finally the third thing you need to know is this thing in the box just up here, that the singularity category and the co-singularity category work that way. So I suppose, just for simplicity, I should take a copy and put it down here. Okay, so that's all you need to know from the first half, I think. Okay, so the subject of the first half is now we're going to take, consider an example. Consider a finite group G with cyclic Sylow subgroup, cyclic Sylow P subgroup. And we're going to work out what the singularity category is in that case. So the cyclic Sylow P subgroup is going to be called C, and which will be cyclic of order P to the N. And let's just make the general observation that we might as well suppose G has got a very special structure. So in fact, if I've got BG, or if I've got G, I could take the normalizer of C, and that would induce an isomorphism in mod P cohomology, and then I could factor out, I'll put a tilde there, or I could factor out the largest normal P prime subgroup, and that would be a mod P cohomology isomorphism, and then this would be a semi-direct product of C and a D, where D is also cyclic. D is cyclic of order Q, and it acts faithfully on C. So Q divides P minus 1. So this is a complicated way of saying, without loss of generality, G is of this form, and I'm going to stick with that. So if you didn't like that bit, just this is we're looking at this example. So let's just, to avoid trivial cases, we don't want p equals 2, because then q would have to be 1, and we'd be talking about a p group. So q is greater than or equal to 2, and p is not equal to 2, just to avoid trivial cases. And just so we really know what we're talking about, examples, we might have G to be symmetric group of degree 3, or I suppose I ought to just say more generally, dihedral of order 2p. So p is p, here is q is 2, and or you might want to think about one of the non-abelian groups of order pq, like order 20 Frobenius group, or anyway, there are lots, and just choose the one you like. So we're going to work out the singularity category. Let's first of all just work out the cohomology ring. So of course, the one thing I do assume you know is the cohomology of the cyclic group. So that's p is odd. So this is a polynomial on a degree 2, tensor exterior on a degree 1, which I'm going to call x and t. So how do I get the cohomology of BG? Well, this is the cohomology. I take the invariants under D, and so D acts to multiply T by a qth root of unity. So this is just polynomial on a capital X, tensor exterior on a capital T, where now capital X is the qth power of little x, and capital T is x to the q minus 1 times t. So x is the degree 2q, and t is of degree 2q minus 1. So this is a very nice, I mean, it's not polynomial, but it's not that far off. So how about this is the point at which you can calculate, you can find out what this BG P completed looked like. So you could use the Eilenberg-Moore, which I even wrote down, which would mean I'd do the X over the cohomology ring BG, and then of k into k. You can work that out, a matter of algebra, and these, in almost all cases, the spectral sequence will collapse. And what it means is that I get, corresponding to polynomial tensor exterior, I get exterior tensor polynomial, which I'm going to, my Greek and Roman alphabets are supposed to correspond. So psi is now in homological degree 2q minus 1. So I'll put a square box around it instead of a round box. And then tor is of homological degree 2q minus 2. And that's true except for the symmetric group of degree 3. So except for G is sigma 3, where you get a slightly different answer. You get k of psi and tor modulo what? Psi squared isn't 0, it's tor cubed or something like that. But anyway, let's not worry about that case. We've got, that's what we have. Okay. And well, so I'm now going to remind you what of the things I said we'd use. So well, I don't know if perhaps we should already call this a theorem. The singularity category of the cochains on BG, this G, well, I was quoting this result, so it's the co-singularity category of the chains on loops on BGP completed. So now perhaps this looks less scary because we know that chains on loops on this thing is just polynomial tensor exterior. And the co-singularity category, you remember, was finitely generated modules, modulo finite dimensional ones. And we can see now that I've written it down, the homology of loops on BG could be completed. It's polynomial tensor exterior. So if I'm just going to allow myself copies of K, extra copies of K, that's essentially allowing me to invert Tor. So this is the same as the bounded derived category of chains on loops on BG P completed, but now Tor is inverted. So this thing in here, I mean, of course, this is, it isn't the same as the polynomial ring. It isn't the same as, but it has cohomology, K of Tor and Tor inverse. So this looks like exterior tensor Laurent thing. So it's supposed to look quite easy. And yeah, maybe I'm worried about the time, so I'm going to state the theorem in here right now. And some of it we'll talk about and some of it we won't get to. So in fact, it is a finite Kroll-Schmidt category. And with Q minus 1 times a new number H minus 1 in decomposables, which I'll introduce, where H here is P to the N minus P to the N minus 1 over Q. So, and well, this is a triangulated category. So there is a shift functor, and there are, and how many orbits under the shift? H over 2 orbits under the shift functor, under shift. And yeah, maybe I also want to say that actually we know it's Auslander, right, and quiver. So, and which is I'm not T to the mod B, where B is Q minus 1. This is an H. So in other words, it's got, it's a cylinder with height H minus 1 and circumference Q minus 1. So obviously this won't make sense to everyone at the moment, but I'm just trying to make the point that there is we rather completely understand this category. And I will introduce some of these things as we go along. Okay. So that's what we're aiming, and I suppose I should definitely put this. This is in the last of those preprints there. So, I mean, what you probably notice, I'm using some. I'm abbreviating. I've got these numbers H and B. This is because cochains on BG is an A infinity algebra, which is amongst a family of A infinity algebras, which are parameterized by two parameters. Well, actually, they're L and A, and which it's about their cohomology ring, which is polynomial tensor exterior, and it's about the fact that there is a Massey product, which is a suitable power. But those will all come up in the description. Okay, so here's the warm up. So, I mean, in particular, there are finitely many indecomposable. So I think that's already slightly surprising. Let's think about the singularity category. This is warm up. Instead of thinking about this complicated thing, cochains on BG, let's consider the singularity category of just the cohomology ring of BG. That's polynomial tensor exterior. So probably people in the audience are more used to working with singularity categories than me, but what do we know in the singularity category? The singularity category, we know that the ring is viewed as trivial. I mean, cohomology of BG is trivial. So for any module, which I'll M, I can map onto it with a free module, and then the kernel is usually called omega M, and because it's a submodule of the free module, the action of the polynomial generator X, capital X, is injective. So this is Cohen-Macaulay. It's a maximal Cohen-Macaulay module, and these have been classified. So indecomposable MCMs over this ring have been classified, and well, so they're easy to say what they are, and in fact, and they are the ideals MI, which is X to the I and T. So you remember we're working inside K of X tensor exterior of T on 2Q and 2Q minus 1. And the range, of course, is between 0 and infinity inclusive. And well, because this is cohomologically graded, so I'm going to cohomology gradings are going to be negative homology gradings. So here's a picture of the whole thing. I don't know, I should probably choose a specific value. So this is 1 and x squared and x cubed, and then it's t and xt and xt squared. So we're looking at something really quite concrete. This is M0, which is the same as the ring. And then M1 is this one. And then M2, whoops, is this one, and so forth. So they're quite concrete things. And I think I want to, so in particular, there are infinitely many of them. Now let's see if we can understand the structure a little bit. So note, well, as you can see from my picture, here we've got M0, and inside there is M1, inside there is M2, and so forth. That's perfectly true, but I want to think about it another way. I want to say that if I shift Mi so that x to the I is in degree 0, if we take, and I'm going to try doing Mi with this is now an open face Mi. This is sigma, x, you remember, is in degree 2q. So to get x to the I in degree 0, I need to suspend 2qi times, i.e. x to the I is in degree 0. I'll just draw the first couple. So, well, x to the 0 we've done. So, I mean, M0 we've done. And that 1 is in degree 0. And then the way I was drawing it was t. This is open face M0, but open face M1 mess that up. Open face M1 now has x in degree 0, and so t was just above it. So this is t, and I'll just so we don't get confused, I'll call this t0 and this one t1, and then in M2 I'd have x squared in degree 0, and then well, the way I've drawn it, it would be up here. Oops. And this is what we might call T2. And now you can see I've arranged it so that these are increasing. Maybe with that's inside there, that's inside there. So now we've got, what have we got? We've got M0 inside M1, inside M2, inside M3, and so forth. And so each time I don't add very much. I just add one copy of the field. So I've added here, T1 is new. Everything else in M1 was already in M0. And T2 is new in M2. Everything else was in M1. I suppose I should have, according to the scale I chose, where Q was 2, most of the things are blank. Okay. And what are the quotients? Well, the quotients are, well, we just need to think about what degrees they're in. So M1 mod M0 is T0, which is actually in degree 1, M2 mod M1, and so this is T0 if you like, and this is 2Q plus 1, that's T1, and this is 4Q plus 1, which is T2, and so forth. Okay, so the conclusion is, i.e. M, I think it works out better if I say Mi plus 1 is M0 union, I'm going to use topology notation, so this is a 1 cell and a 2Q plus 1 cell, and then all the way up to a 2QI plus 1 cell. Okay, so this is what I wanted to get to, and of course in the singularity category, so in the singularity category in dsing, M0 is trivial. So all of these modules are just formed by starting with K and sticking on more copies of K. So Mi plus 1 is formed from nothing by with, let's say, with, I suppose there are actually I cells. Okay, so that was supposed to be a warm-up, and now I want to try and do the same thing for cochains BG. So now work with cochains BG modules. Now, of course, it's slightly different because our cochains BG modules, cochains BG, probably it's a ring spectrum. I don't really know, what the, I haven't got elements of my objects, but I do know I want to construct objects with the cohomology, which are the MIs. So, and aim to construct objects. Well, oh dear, I wanted to call them MI. Maybe I can do something else. I'm going to get an extra bar with pi star. Mi is Mi, if that's not too confusing. Okay, and we're going to do the same thing. We're going to start with, so M0, of course, is trivial. Because it's supposed to have homotopy, which is a free module. And then M1 is also easy. I'm just going to start with a copy of K in degree 1, because we know what K is. So now how do I form M2? Well, I just notice that all I need to do is stick on another copy of K. So this M1 is suspension of K. And then I want to attach the new cell in degree 2Q plus 1. So I'm going to try doing sigma 2Q of K, and I want to take its mapping cone. So so here I need a map from sigma 2QK to K, and then I'm going to take the mapping cone and make it M2. That's what I want to do. So what should question mark be? Well, we better think about what are the maps in the singularity category from K to K. Well, we know that because well, because it is the same as, well, there's two. I mean, what is hom over cochains BG K into K, whose homotopy is going to be maps from K to K in cochains BG modules? This was chains on loops on BG be completed at P, which we just worked out what the homotopy of that is, and it was the homology was it was polynomial tensor exterior, so that's exterior on a psi tensor polynomial on a Tor. And then, but we passed the singularity category, which had the effect of inverting Tor. So this is exterior on psi tensor K of Tor and Tor inverse. So then we have to remember the degrees of these things. Psi was supposed to be of degree 2q minus 1, and Tor was notice had a square box around it, and Tor was 2q minus 2. Okay, so obviously we want to take question mark as psi. So how am I going to write that? I'm going to say equals psi. Ah, I see, I run out of time. Very good. Well, I'm going to go just far enough to say where the problem comes. Okay, so now we're going to repeatedly do this. So we formed M1, which has got one cell in degree 1. I've just told you how to make M2 with a cell in degree 1 and another one in 2q plus 1, and that was attached with a psi. And then I want another one with a cell in degree 4q plus 1. And of course, I'm going to attach that by psi as well. And I'm going to carry on going. And I'll just draw the third one. So these are all supposed to be psi. Now, I want to just carry on going. And I could carry on going when I was talking about the cohomology. But now I can't just do this because there's an obstruction to forming the next one. So you can see this was M2. And this was M3. This is M4. So I mean, to form M3 from M2, it's easy to see that you need psi squared, so it exists since psi squared equals 0. Of course, it doesn't always exist because for the symmetric group of degree 3, psi squared isn't 0. So if not sigma 3, since psi squared is 0. But M4, why does that exist? It exists if the Massey product psi is 0. Okay, so now I can keep on going until I get a non-zero Massey product. So now I'm just going to write down this theorem and then I'll stop, which is that in cochains BG, we have some Massey products. We have, well, these are capital T. The first non-zero Massey power of T's is the p to the nth. And the answer is the hth power of x. So I've introduced p to the n is p to the n, the p dividing the order of the group, and h was this thing, p to the n minus p to the n minus 1 over q. And then in chains on loops on BG, be completed, we have psi, and this time we have the hth power, and that is minus Tor to the p to the n. And so that shows you, hence, M0, which is trivial, and then M1, and we keep on going up to MH exist, and MH plus 1 and higher, H plus I, does not exist, or I greater than or equal to 1. So that's at least a construction of some indecomposables. How do you prove this theorem? So the first half of the theorem is an easy consequence of very classical results. So for the cyclic group C, Cranes showed that the p to the n fold Massey product was the first non-trivial one. It was on the degree 1 generators, the first non-trivial one, and it was minus x, where that was little x. And so all I have to do is just take that formula and look what it means inside the cohomology of BG, which was a subring. To get the statement in for the chains on loops, what we've got to do really is do causal duality for A infinity algebras. So, I mean, as a topologist, I prefer to do it as in a different way, but what we actually needed to do was to be quite explicit and use some additional gradings to let us make some calculations. So it turns out the A infinity algebras for cochains on BG and chains on loops on BG, they are, they're the only ones. We don't know this. We believe that they're the only a non-trivial A infinity structure on something with polynomial tensor exterior with these degrees. In order to, we didn't quite prove that because we used some additional properties using the fact we got an additional grading. But I think we believe that they are the only ones, and perhaps someone will tell me that's true. I'm sorry, I've gone way over, and so I'll stop. Thank you.
Thank you so much. Are there any questions? There was one request for a question about this BGG correspondence and like one of your results with Greg. Would you mind pulling it up? The BGG.
So would I've got to do something, have I?
Or just the question was about the BGG correspondence, like one of your results with
Oh,
Greg.
I see. Okay, good. So we can go. Now I know what you mean. This one.
Yeah. So the question is that the one of the left-hand side doesn't seem to depend much on the field, whereas on the right-hand side, you have to complete with respect to P, and if there was there was an explanation there, or
okay, good. I mean, so that's because of the condensed notation. So cochains BG is shorthand for cochains BG with coefficients in K, which explicitly meant the mapping spectrum of BG maps from BG to Eilenberg-MacLane spectrum. And the point is that the map from BG to BG completed at P induces an isomorphism, or sorry, a weak equivalence, an equivalence of these two cochain things. And so on the left-hand side, there's no change if I go from BG to BG completed at P. However, the Morita theory required the Eilenberg-Moore spectral sequence to converge, and the Eilenberg-Moore spectral sequence only converges if you could feed it a complete thing. And I mean, you can try doing it with a non-complete thing, and you don't get the right answer. I mean, because for example, we did it when G had cyclic single P subgroup, and when we did the Eilenberg-Moore on polynomial tensor exterior, we got polynomial tensor exterior. So in particular, it was not in the finite range of degrees. So I didn't get the homology of loops on BG, which is G, which is a collection of points.
I think that helped a lot. Yeah. Any other questions?
Maybe just a comment that I remember Rukiye telling me something about, you know your A infinity algebra at the end?
Right, yeah, that's right.
Yeah, I remember Raphael telling me something very, very similar to it, what it seems that you want. I can't remember whether he was making the same hope, expressing the same hope, or stating a fact, but
yeah, I mean, so how this I can now say what they, I mean, I probably, you know, I can look at K of X tensor exterior T. So this has got let's have this is of degree 2 minus 2a, and this is of degree minus okay, so we've got a polynomial tensor exterior, and then we've got the ring structure, which gives us an M2, and then I've got a p to the n fold. So we've just got M2 and MP to the n, and those are the only non-zero ones. And that, yeah, and I think you can show that those are the only, then you can put the MP to the n into standard form as done here. But then showing that that's true for the causal dual, that we use some additional properties. We use the fact we could do some representation theory of the groups, and that fed through. Because I mean, we got this process by you start with KG, then you form the X algebra, cohomology of BG, and so that's a causal dual. And then you do the second dual, you get chains on loops on P completely classified space. You don't get back where you started from. You get back to some sort of completion, but still the structure you had for KG, because you, or rather Dave, knows the representation theory of this group so well, you just spot this additional structure, which you can use which you can carry on through and to get to the other side. And that's definitely something. I mean, all these things which are special for this group, there's lots of things you'd like to do in general, but at the moment, they rely on some rather special calculations. And I think you need to work harder to be able to show that they hold more generally. But anyway, did Rukiye point to something for this? Because he may well know this fact.
I just remember a conversation about this kind of structure, and so it might be worth trying to ask him.
All right. If there's no more questions, let's thank.
I have a question.
John.
If there's
Chris.
there's
Yeah,
time.
go ahead. Sure.
So, what's the relationship between this singularity category on the chains on BG and the stable module category of G, like with respect to the same prime?
Great. So I'm glad you asked that too. So if I'd had the co-singularity category of cochains on BG, the singularity category, very good. So if I'd taken the singularity category of KG, no, this would be the same as the stable module category, or stomod of G, because it's a bounded derived category modulo the free modules. So this is supposed to be related to the co-singularity category of the cochains on BG. I mean, okay. So you can start with BG. You can take causal duals, and so you get cochains BG, and you can take causal duals again, where the operation x to this is homs over x of k into k. And then I can do that again, and I get chains on loops on BG completed. So this was cochains BG, exclamation mark, which is that. So I've gone in 2 steps. I didn't get back to where I started from because the Eilenberg Moore didn't converge, or for some more profound reason. And you're asking, no, because causal duality is perfect here, I can go backwards again. You know, if I do it again, I get to there. So I go round and round. Because of that, there's d sing of cochains BG is d cosing of chains on loops, and d cosing cochains BG is d cosing of chains and loops. It's annoying how many brackets you need to write. And then there was the related thing, d cosing of kg and d sing of kg. So I don't understand the relationship between there, but there's some relationship. And you were asking about the singularity category of kg, and so it should be like the co-singularity category of cochains on BG. But working out the exact relationship is of great interest. I mean, you could also do some of these things with, I don't know if anyone cares about things like connective K theory and topological modular forms, but you can sort of relate the singularity category, the co-singularity category of those, because they're regular, so the singularity category is trivial, with the singularity category of their endomorphisms, which are like the Hopf algebras A1 and A2, the Hopf subalgebras of the D-nod algebra. So it's like saying the stable module category of KO is something like the co-singularity category. Of A1 of KO, and then and I better put inverted commas so that you don't take me literally. So this is another example of the sort of thing that you're saying. I know it's still, I mean, the inverted here actually, these are facts. It's just you need the inverted commas to explain what you're talking about. And at the moment, it just means it's a ring spectrum whose homotopy is the thing inside the inverted commas. Phi star of A is A.
Thank you so much, John. Let's thank John again. It was a wonderful talk. Thank you so much.
Well, it's been great to be with you. Well, I look forward to seeing you in person at some point.